All right, this is Mr. McMurray, and going back to wheel and axles, I know what I was talking about. If you look at a bicycle, question is, are those considered wheel and axle? Well, actually, it turns out that the front wheel is not, even though it has an axle and it turns, but you don't turn the axle and make the wheel turn. Okay, it actually gets pushed by the back wheel. Now, the back wheel, you push on the pedals, it pushes on the chain hits the gears on the back, and that turns the axle, which turns the back wheel. So the back wheel on a bicycle is actually a wheel and axle, but the front wheel is not. Same would be true if you had, say, front wheel drive. Your front two wheels would be a wheel and axle, whereas the back two wheels would just get pulled along for the ride. Vice versa if you had back wheel drive. Now, if you have all four wheel drive, then they would all be considered acting as a wheel and axle. A wheelbarrow, on the other hand, when you roll it on the wheel, you're just pushing the wheel, so you're not turning the axle to make the wheel turn. So that, once again, even though there's a wheel with an axle, it is not a wheel and axle simple machine. All right, let's get back to where we were. So all simple machines can either be classified as a lever or an inclined plane. All right, on a pulley, we said in the middle you have an axle, and if you think about it, the pulley spins around the axle, so that would make it a fulcrum, so to speak. If you drew a straight line through the pulley, as the pulley goes around, it would be like tipping a lever. Okay. However, the difference is, whereas a real lever would just fall off once it got to the side, this one just keeps going around and round and round. So it's kind of like a circular lever. Okay. Same thing when you use a screwdriver. It rotates around the center of the handle. Okay. And so it is kind of a same thing. That's the fulcrum, is the center of the handle right there, and it tilts around. It just keeps going around and around and around. So it's also another type of circular lever. Okay, so very good for there. All right, sir. And so we can say that both. Maybe let me find my thing and we'll click. Why we're not clicking. There we go. All right, pulleys and wheels and axles could both be considered circular levers, and the fulcrum would just be the axle. Okay. All right. Then screws and wedges. We already talked about how a inclined plane wrapped around a post basically makes threads or a screw. So that's basically just a inclined plane wrapped around it. And if you put two inclined planes together so that they came to a point, all right, that would be a wedge. So those are really just kind of inclined planes, and we kind of said that when we defined them. All right. Now, most machines have more than one machine. They have several parts put together. So, for example, on scissors. All right. So on scissors, you have a fulcrum in the middle right there, so it acts like a first-class lever. But you also have blades at the end, which would be an inclined plane or a wedge. Okay, and so that's two machines put together in one. If you take a can opener, okay, well, when you clamp it down, you bring it down like this. There's a fulcrum down here, so it's a lever. All right. Then you turn the handle, which turns the little wheels and turn it right there. Okay, so that would be like wheels and axles. All right. And at the top, you have a blade that cuts down into the can, so that would be like a wedge. So basically, it has three machines, all for the price of one. So that would be a compound machine. All right. Bicycle has levers and the handbrakes, and with the brakes actually squeeze the wheels, another lever. And they also have wheel and axle, obviously, from the pedals to the chain and to the back wheels. So all of those make it a compound machine. All right, mechanical advantage. Mechanical advantage we talked about before. It says how many times the machine multiplies your effort force, okay, or how many times easier is it for you to use the machine. All right, and so there are actually two types of mechanical advantage we want to know. One is the ideal mechanical advantage. In a perfect world where there is no friction or anything like that, all right, so that would be the ideal mechanical advantage. All right, because there's no friction, no loss of energy, and that would be how many times it helps you in a perfect world. And since we're doing that, we don't measure it by doing the actual force. We do it by comparing the distances. Okay, effort distance, how far it moves, divided by the resistance distance. Okay, would be one way to do that. Or, like we said on levers, the effort arm, the longer it is, the easier it is to use. So this number is bigger and the resistance arm is shorter. Then the longer the effort arm, the more the mechanical advantage. All right, now to do the actual mechanical advantage would be the mechanical advantage with friction. Then we actually do it and we see how much force can we move and how much effort force does it take to move it. Okay, so for example, if something has a force of 100 newtons and it only takes me 25 newtons to move it, it'd be 100 divided by 25. That gives me a mechanical advantage of 4, which means I only have to use 1/4 as much force, and it's 4 times easier to move it than it would be if I had to lift the whole weight. All right, that's basically it. And so if you'll answer the questions, and then next time we will have a quiz for you.